For the next part of this tutorial on classes, we're going to cover something called Langton's ant. So if we just pull up Langton's ant here on Wikipedia, we can see the general structure. Langton's ant is a two-dimensional universal Turing machine with a very simple set of rules, but complex emergent behavior. We can see in the rules section here, relatively straightforward rules. So squares on a plane are colored variously, either black or white. We arbitrarily identify one square as the ant. The ant can travel in any of the four cardinal directions at each step it takes. The ant moves according to the rules below. At a white square, the ant will turn 90 degrees clockwise and then flip the color of the square and move forward 1 unit. At a black square, it will turn 90 degrees counterclockwise, flip the color of the square, and move forward 1 unit. So in both of these cases, it's going to flip the color of the square, move forward 1 unit. It just has a different turning rotation. You can see in the example file, I have one already built, but again, I'm going to just build one from scratch for you. So double click, type gh-python, and now we're going to change these inputs and outputs eventually, but for now I'm just going to call this Langton's ant. Okay, and we're going to need to import Rhino script syntax, script context, and we'll say sc.equals gh-doc in case we've changed that in another file. It's always a good habit to be in to always start off with that. So it says here there are squares on a plane which are colored variously, either black or white. We arbitrarily identify one square as the ant. The ant can travel in any of the four cardinal directions at each step it takes. Okay, we need two things then. We need a territory or farm for ant to exist in/on, and we need ant arbitrarily. So those are the two things we need. In this case, we're going to use classes to define each one of those. This way we can embed properties to each of those things. So properties to this kind of farm or territory, and properties to the ant itself. The first thing we're going to start with is the territory, which it says are squares on a plane colored various. To me, this sounds like a mesh plane. So we're going to use a mesh plane to start to build this. So in Rhino, type mesh plane. Well, maybe for now we can just set this lower. So set the resolution in the XY to 20. Start at the origin, and we can say make it 10 by 10. Now we need to set this as an input to this component. So if we right click on this X, change this to capital M, double click, type mesh, and we're going to set this mesh. So right click, set one mesh, and we've now set that mesh, so we can click and type hide in Rhino to hide that mesh. I'm also going to disable or hide the preview inside of Grasshopper as well. Okay, so we've now fed in this mesh. What we want to do is create a class. So start by typing class, and then we're going to call this class ant farm. In this class, what we need to do is input the mesh as our kind of territory or farm for the ant to operate on. And we need to extract a few things from the mesh in order for this to work. So if we start with a constructor function, so def underscore underscore init underscore underscore, and then self, we're going to input the mesh ID. Now we can close this parentheses, hit colon and enter, and we're tabbed into this constructor function. From this mesh, we need a couple of things. So first we need the self.id of the actual mesh. So self.id equals mesh ID. And then we also are going to need the point array. So we can call this self.vertexes and equals rs.mesh vertices, and we are going to use the vertices from the mesh ID. One more thing that we are going to need is the states. It says that this mesh should be arbitrarily colored with white and black squares. So we can say self.states. So we want these states to be the same number as the vertices. So each vertex, or essentially square, let's say face, but in this case we're using vertexes, Each vertex on the mesh is going to be a different state, which will eventually become a different color, white or black on the mesh. So instead of just creating an empty list, we can say a list of 0, and outside of the brackets, we can type asterisk, so multiply by length self.vertexes. This is going to create a list of zeros with a length of self.vertices. So test this by just printing self.states, or rather, let's try length of self.states, and then we can just print the first item to make sure that they are all 0. So self.states 0. Now, down here, we're going to want to call this, otherwise it's not going to run. So let's just go ahead and call ant farm, and we can call this my ant farm equals ant farm, and we need to feed in the mesh ID, so m. Now hit test. So it prints length 41. Let's also just go ahead and print length self.vertexes. So we have 441 vertices and 441 states. So this worked perfectly. So for now, we're done with our ant farm. We can come back to that in a second. Now, the next step is to construct our ant. So first we want to build the class ant. And in this case, we still want to feed self. We always have to. We need to feed in an arbitrary point on the mesh is what the page said describing Langton's ant. So let's feed in a position or coordinates of a point in space. Then we're also going to need to feed in a heading so that it knows where to start heading towards. So that's going to be a vector. And then the last one is going to be the index that it is on. So this is going to be the index relative to the mesh vertices. Let's index. And now we need each one of these inside of the constructor function as a property of this class. So self.pos equals POS, self.vec equals vec, self.text equals index. Now we need to make an instantiation of this class, my ant equals, and this is going to take those 3 input parameters. So that's input point. We now need to feed that in inside of Grasshopper, point parameter inside of Grasshopper, and then set 1. We want to set this somewhere on the mesh, so there you go. Point on the mesh, and that is set as our input point parameter. Now, we also need a vec and an index. So what we want for those vecs and index is the direction of the next point on the mesh, not the current point that the ant is on. So the first thing we probably want to do is make sure that this point exists on the mesh, and then we want to look for the next point on the mesh to create the vector heading of this ant, and then we will use what point it is on, or the index relative to the ant farm, to check the state and then change the state. So the first thing we want to do is above here, we want to basically get not just the point ID, we don't need the point ID, we need the coordinates of the point. So we can say LOC or loc equals rs dot point coordinates of the point. We need the index value of the closest point on that mesh, so the current point that the ant is on. So this is going to be index equals rs dot, and there's a function in here built into the Rhino script library called point array closest point. And if we open up the parentheses there, we see point array closest point finds the point in a list of 3D points that is closest to a test point. It takes as input the the cloud to search from, so the cloud of points to search from, the cloud of points to search, and the test point to search from. So in this case, our loc is going to be that test point, and our input points are actually going to be my ant farm.vertexes. So we're going to allow all of the vertices to be searched from the location. And then our last one is going to be vector, so vec equals, and this vector is going to equal rs.create vector. Now what we want to feed in here is a vector from our location loc to the next point on the mesh. So this is going to be our current vertex which we're on, but not using index, instead using index +1, so the next point in the list of indices. And then we're going to say minus location. So this will give us a heading from our current location to the next vertex on the mesh. Now, instead of feeding in point, we will feed in loc, comma, then we see the next one is actually vec, so loc, comma, vec, comma, index. Now hit test, we don't have any errors. It's only constructing instances of these two class objects. If we actually want this to do anything, we need to build a bit more functionality into both the classes. So if we remember back to the description of a Langton's ant, we know that the ant is going to have to navigate around its territory, the ant farm. So just going to clean this up a bit. So we know that somewhere here there needs to be more functionality in this ant to make it actually move. So we can start and make a function. Now we need to feed it at least self. And for now, that will be it. And then we know somewhere down here, we need to call that function. So we need to call move ant at least one time so that it runs the move function. The rules for navigation in a Langton's ant, it says in our page here, is at a white square, turn 90 degrees clockwise, and at a black square, turn 90 degrees counterclockwise. Flip the colors of both and move forward 1 unit. Okay, so this is pretty simple motion, but what we need to know is the states. We need to know a rotation value or rotation vector, and then we need to add that to our current position so that it can then move forward relative to that rotated vector. So first we're going to need states, but we don't actually care about all of the states in our ant farm. Instead, we just care about the one that is on our current index. So that's this index. So we're going to want to use my ant farm dot states, and our current state, which will feed in self.index, this current state relative to the current vertex we are on. Now, if we test this and hit print state, run the test, we can see that our state is 0. Now, if we want to rotate relative to this point in space on the ant farm, we're also going to need a normal, which is the direction that the vertex faces on the mesh. So in this case, all of them are going to be straight up. It is also a vector in the z direction relative to the current point the ant is on. So normal equals, and then we're going to need a new property here. So my ant farm dot normals, and we're going to feed in self.index as well. So now if we go back up to this constructor, we need self.normals equals, and we can just say, maybe move that up here underneath the vertices, rs.mesh vertex normals. Then this takes a mesh ID, so mesh ID. Okay, so now we have a state and a normal based on our current index value. So now that we have the normal, we need to build in the actual rules for motion. We know that if the current state is 0 or black, we need to turn clockwise 90 degrees. So this will mean that we need a conditional statement. So if state equals 0, then we are going to rotate about this normal. Then we're going to rotate clockwise 90 degrees about this normal. So what we need to do is update our heading, and then we're going to add this heading to our position so that we can actually move forward based on that rotated heading vector. So we are going to say self.vec, which will allow us to update that self.vec equals rs.vector rotate. This function takes a vector input, an angle in degrees, and an axis. So we will give it self.vec as an input, and then we need 90 degrees as an angle, and the axis we are going to use is the current normal. Now, this page also says that we need one other thing, which is to flip the color and then to move forward, which is adding that vec to the component, but flip the color of that square or change that state. So what we are going to need is myandfarm.states.self.index, and we are going to now set this. If it's 0, flip it, so change it to 1. Now we can say else, because if it's not 0, then we know, or black, then we know that it is white or 1. And then we're going to have the same rule here, but just a negative 90 degree rotation. And then we're going to copy this as well and flip it to 0. So the next thing we need to do is to create a temporary position. So temp pause, and this temporary position is going to be set equal to rs.pointAdd, and we are going to use our current position, self.pause, and we are going to use our self.vec, our new heading vector. Now we need to update our index as well. So self.index equals rs, and we are going to find the closest. We're going to find the closest point in our point array. So closest point, input point, and test point. So this is going to take the vertex list from the ant farm. So we're going to say my ant farm dot vertexes, and we want to feed in all of those vertexes and then pause as our point to search from. We need to update our position as well. So self.pause, updating the ant's position, equals, and we're going to set this equal to my ant farm vertexes of self.index. So the new position equals the current vertex related to the closest. Now, if we hit test, this should work and be running, but we don't actually have a printout, but this should be the structure, so our ant should be able to move now. All we want to do though is make sure that we are actually rendering this. So now we have to build a render function, a way of visualizing this. So we're actually going to do that inside of the ant farm because it's the ant farm that we want to visualize the change in colors on. So if we hit enter, backspace or tab out 1, and then make a new function called render, we need to feed in self. And what we want to do here is cycle through each of the states. So each state in this list of states, which corresponds to a vertex. And we want to color that vertex so that we can visualize it, and then output it into our Grasshopper window so that we can actually view the output. So the first thing to do is we are going to make a blank list of colors, and then say for state in self.states. So reading our list of states here, for state in self.states. Now we are going to say if state equals 0, colors.append, create color, and we are going to append a black color value. So 0, 0, 0. Else colors.append. Here we're going to create a white color value, so 255 is the full range of the color spectrum. Okay, so we've now appended those to our list of colors. If we want to check, we can print colors here. So before we actually check those colors, we need to call this function. So if we just scroll down to the bottom, we can create a call below the move ant. So first we want to move the ant as many times as we want, which right now is just 1. And then we want to call my ant farm, because that render function is inside of the class instance, the class ant farm. So my ant farm dot render. Now if we hit test, we can see that it's printing out the color objects from that colors list. So we've created that list of colors. Now we just need to apply those colors to the mesh. So if we just tab out here, but still in the render function. So in order to apply this to the mesh, we can type rs.vertex colors. And we can see here that it takes an input of a mesh ID and then a list of colors. So a list of color values is that colors input. So first we need our mesh, which is going to be self.id, this self.id mesh ID. And then we are going to feed in a list of colors. Now what we need to do is reference this later in our script after we've called this render function. So that property, we just need my ant farm, so my ant farm, and then .id, and this is going to be the ID of our mesh. And then we can just say maybe out equals that, and then just copy m out, right click on this A, and we can set m out equal to the output parameter. And now if we hit test, we can see that every state on here is going to be 0, black, except for the one that our point is on. We've only run this Langton's ant once, so we've only run the move one time. Now, hopefully this is familiar by now, but one way that we can do this multiple times is to loop through this movement. So for I in range 100, my ant dot move ant. Now we can hit test. If we increase this even more, so 1,000, we can see that it quickly expands. We can also increase the resolution of this mesh. So if we just type mesh plane, increase the resolution to maybe 200 by 200. Now we have a denser mesh. We can right click, set one mesh, and our ant is running on this mesh and we are rendering it. So you'll remember in the description it says, so the first few hundred show simple patterns, often symmetric. Then after a few hundred moves, you start to develop chaotic patterns. And then after around 10,000, you start to get patterns of emergent order. So right now we're running 1,000. If we decrease this again, let's say to 10, maybe we need more than 10, 60. We have a simple pattern. Then let's say 400. Seems to be still a pretty ordered pattern. Maybe let's try, this is maybe approaching chaos, but let's try 6,000. Now we're starting to get into the realm of actual chaotic patterns. And then if we go above 10,000, so 12,000, we should see some emergent order and highways developing. So we do see one here developing. Now, we could output this mesh and just bake it if we wanted the output from this run, so this Langton's ant. But right now the output is just the colored mesh. So there are two more things that we could do. One is related to the input setup, and if we wanted to input multiple ants instead of just one. And then the other is ways of capturing other data from this. So one example is we start with an initial location and then we end with this output location, and it's kind of trail drawn out in color. But we can also represent this trail as an actual curve. So what we need to do for that is update our properties inside of the ant and add something called trail points. And right now I'm going to just set that to an empty list. But every time we perform the ant movement, we can just append this self.pause. And then at the end, we can render this curve. So we can say T equals my ant trail points. And this is just going to give us the list of points. But if we want, we can actually add a curve or a polygon curve from these points. And then we just need to add that as an output here. Right click, capital T is our out. And this now gives us an output curve. So we can see that output curve drawn over our mesh. If we just want to visualize the curve, we can bring out a curve parameter and then hide the preview on our component. So this is the trail of the Langton's ant. For now, I'm just going to comment that out so that we don't process that. So the next thing we want to do is, instead of just feeding in one single point, so right now we're just instantiating one instance of the class ant, we actually want to feed in multiple starting points. So if we just go ahead and right click on this point parameter in Grasshopper, set multiple points, and then click to add multiple points here onto our mesh and then hit enter. Right now it's just going to run as 5 separate instances. So we can actually see now we get 5 mesh outputs. So this is because this point parameter on our component, so this input parameter, if we hover over it, says 5 inputs. And then if we right click on this, we'll notice that this is set to item access. So this means it's going to read each item in a list, if we give it a list, as independent inputs. So it's actually running this component 5 separate times and then outputting each output from each run. So this isn't exactly what we want. We actually want the ants to be running on the same mesh. So we can just say list access, and this allows each of the meshes to run at the same time. Now we're getting an error because we're inputting multiple points into a parameter that in Python should just be one single point. So right here, location equals rs.point coordinates from point. So actually what we need to do is we need to say this is points input. We need to say 4 point in points. And then we want to tab all of this in. So for each point in the list of points, we need to find the location, we need to find its closest index, and we need to create a vector heading. This means we also need to tab in this myAnt. So now we have all this tabbed in. It's going to loop through each of the points in the list of points and create a new instance of the class ant. But if we run this, so if we just hit test, we see that it's still only using one of these ants. So it may be running through all of the points here, but it's not actually running through each of the moves. And in order to do this, we actually need to create something called a population. So this is going to be a list containing all of our instances, and we need to append to population our instance of that ant. And then inside of this range, which sets the number of iterations for the Langton's ant, we need to say for my ant in population, my ant dot move ant. Now if we hit test, we can see now that they're all drawn on the same mesh output. We're visualizing them together, and actually if we increase the iterations, we should see them start to interact. So they're a bit too far at that point, but if we go all the way to 15,000, we should see them starting to interact on the mesh. So now we can see those interacting there. But if we wanted to use our trail output, we're going to have an issue because they will all be linked. So this is only going to render the trail for one ant. If we wanted to use this trail output properly, what we would need is to actually cycle through, similarly to what we're doing here, the list of trail points. The best way to do this is to actually loop through each of the ants and render out the trail specifically to each ant. So if we set t equal to an empty list, then we say for my ant in population, similar to what we did up here, but instead of move ant, we're actually going to use the function my ant dot render, and then we are going to append this output, which we can just directly place inside of there, to the list of trails. Now we can copy this line, and we're just going to move that into a separate render function inside of each agent. Def render self. But if we want this to actually output into our append right there, then we need to return this data outside of the function. So we need to pass this outside. So we use a return to pass items outside of this function. So now it's going to render this using not my ant, but in this case self. So self.trailPoints, and it will make an interpolated curve relative to each one of the agents, which is important. Now in this case, I'm going to just lower this down to 10,000 so that it runs slightly faster. Now hit test. And now we can see each one of those curves, and we should be able to see, yep, 5 planar curves output from there. If you want to check those or bake them, we can bake those separately and see that there's 1, 2, 3, 4, and 5 output trails. So that is all for the introduction to classes. In the next session, we're going to be adding some functionality to each of our classes.